Yes, it is permissible to install two 300 kc milk conductors in parallel to feed an 800 amp panel board. Each conductor will effectively carry 400 amps. This falls within the ampacity rating for a 300 kc milk conductor, provided the installation meets all applicable code requirements. To calculate voltage drop, a formula can be used: voltage drop equals current times distance times resistance, divided by 1000. In this equation, voltage drop is expressed in volts, current is in amperes, distance is measured in feet, and resistance is in ohms per 1000 feet. The process involves several steps. Firstly, you must accurately determine the distance from the point where the feeder enters the building to the location of the panel board. This measurement forms a crucial part of the voltage drop calculation. Secondly, calculating the resistance of the conductors is essential. This can be achieved using the formula resistance equals resistivity times length divided by area. In this formula, resistivity is a material property measured in ohms per kc mil foot. For copper, a common conductor material, the resistivity is approximately 10.37 ohms per kc mil foot. Length is the length of the conductor in feet, and area represents the cross-sectional area of the conductor in kc mil, or thousands of circular mils. Thirdly, with the current, distance, and resistance values determined, multiply these values together. Subsequently, divide the result by 1000. This calculation yields the voltage drop. Consider an example where the distance from the building entry point to the panel board is 100 feet. Assuming the resistivity of copper is 10.37 ohms per kc mil foot, we can calculate the voltage drop for the two 300 kc mil conductors in parallel. Voltage drop equals 800 amps times 100 feet times 2 times 10.37 ohms per 1000 feet, all divided by 1000. This equals 0.166 volts. Therefore, based on these calculations, a voltage drop for the two 300 kc mil conductors installed in parallel is minimal, at 0.166 volts. This level of voltage drop is generally considered negligible and should not pose significant concern for a feeder supplying an 800 amp panel board. However, it is always important to verify that the calculated voltage drop meets the requirements outlined in the applicable electrical codes and standards to ensure optimal performance and safety of the electrical system. These calculations also have to be verified to ensure the values match the requirements set forth in the National Electrical Code, specifically Chapter 9, Table 8. If you are using aluminum conductors, the values will be different. The ambient temperature and the conductor temperature rating must also be factored in when calculating the ampacity of the conductors. When conductors are placed in a cable tray, the National Electrical Code provides guidance on the allowable ampacities based on the specific installation conditions. These conditions include the type of cable tray, the spacing between conductors, and the presence of other heat-generating sources. Ensuring compliance with these requirements is essential to maintain the safety and reliability of the electrical system. Always consult with a qualified electrical engineer or licensed electrician to ensure that all electrical installations are performed in accordance with the applicable codes and standards. The National Electrical Code provides tables for adjusting ampacity based on ambient temperature. Conductors have insulation ratings, such as 75 degrees Celsius or 90 degrees Celsius. If the ambient temperature exceeds the temperature associated with the conductor's rating, a deterring factor must be applied. These factors are provided in NEC Table 310.15 Burn. For example, if you have a conductor with a 90 degrees Celsius insulation rating and the ambient temperature is 50 degrees Celsius, you would use the appropriate deterring factor from the table. It is important to note that the deterring factors can vary depending on the conductor size and insulation type. Furthermore, when multiple current-carrying conductors are installed in close proximity, their ampacity must be derated to account for the increased heat generated. This derating is necessary because the heat from one conductor can raise the temperature of adjacent conductors, potentially exceeding their insulation ratings. NEC Table 310.15 current provides adjustment factors for the number of current-carrying conductors in a raceway or cable. For example, if there are 4 to 6 current-carrying conductors, the ampacity must be derated to 80% of its original value. Similarly, if there are 7 to 9 current-carrying conductors, the ampacity must be derated to 70%. These derating factors are cumulative. If you have both ambient temperature and multiple conductor derating, you must apply both factors to determine the final allowable ampacity. In cable trays, the ampacity of conductors must also be derated based on the type of cable tray and the number of conductors. NEC Section 392.11 provides specific requirements for cable tray installations. For example, if you have a ladder-type cable tray with multiple conductors, the allowable ampacity may be reduced compared to a single conductor in free air. It is crucial to consult the NEC and relevant engineering resources to determine the appropriate derating factors for your specific installation. Proper derating ensures that the conductors operate within their safe temperature limits, preventing insulation damage and potential fire hazards. In addition to ampacity derating, voltage drop is another critical consideration in electrical system design. Excessive voltage drop can lead to reduced equipment performance, overheating, and even equipment failure. The NEC recommends limiting voltage drop to no more than 5% for feeders and branch circuits combined. To calculate voltage drop, you need to consider the conductor length, current, and impedance. The formula for voltage drop is voltage drop equals current times impedance times length, divided by 1000. Where current is the current in amperes, impedance is the impedance of the conductor in ohms per 1000 feet, and length is the length of the conductor in feet. The impedance of a conductor depends on its resistance and reactance. Resistance is the opposition to current flow due to the conductor's material and size. Reactance is the opposition to current flow due to the conductor's inductance. For short distances, the reactance can often be neglected and only the resistance is considered. However, for longer distances, the reactance can become significant and must be included in the calculation. NEC Chapter 9, Table 9 provides the resistance and reactance values for different conductor sizes and materials. Using these values, you can calculate the voltage drop for your specific installation. If the calculated voltage drop exceeds the recommended limit, you may need to increase the conductor size or reduce the length of the circuit. In parallel conductor installations, the voltage drop calculation is slightly different. Since the current is divided between the parallel conductors, the voltage drop is reduced. The voltage drop for parallel conductors can be calculated using the formula voltage drop equals current divided by the number of parallel conductors times impedance times length divided by 1000. Where current is the total current in amperes, the number of parallel conductors is the number of conductors in each phase, impedance is the impedance of each conductor in ohms per 1000 feet, and length is the length of the conductor in feet. By using parallel conductors, you can reduce the voltage drop and improve the performance of your electrical system. However, it is important to ensure that all parallel conductors are of the same material size and length. They must also be properly terminated to ensure equal current sharing. Failure to meet these requirements can lead to unbalanced current flow and potential overheating. In addition to ampacity and voltage drop, other factors must be considered when selecting conductors for an electrical installation. These factors include the type of insulation, the environmental conditions, and the mechanical protection requirements. Conductors are available with various types of insulation such as THHN, THWN, and XHHW. Each insulation type has different temperature ratings, moisture resistance, and chemical resistance properties. The appropriate insulation type depends on the specific application and environmental conditions. For example, THHN insulation is commonly used in dry locations, while THWN insulation is suitable for wet locations. XHHW insulation offers excellent moisture and heat resistance and is often used in underground installations. The environmental conditions can also affect the choice of conductors. In corrosive environments, conductors with special coatings or insulation may be required to prevent corrosion. In high-temperature environments, conductors with high-temperature insulation should be used. The NEC provides guidance on selecting conductors for various environmental conditions. Mechanical protection is another important consideration. Conductors must be protected from physical damage such as abrasion, impact, and crushing. This protection can be provided by using raceways, conduits, or cable trays. The type of mechanical protection required depends on the location and the type of installation. For example, conductors installed in exposed locations may require rigid metal conduit for protection, while conductors installed in concealed locations may be adequately protected by flexible metal conduit. In summary, selecting the appropriate conductors for an electrical installation involves considering several factors, including ampacity, voltage drop, insulation type, environmental conditions, and mechanical protection. The NEC provides comprehensive guidance on these factors, and it is essential to consult the code and relevant engineering resources to ensure a safe and reliable installation. When designing an electrical system, it is also important to consider future load growth. The conductors should be sized to accommodate the anticipated increase in load. This can be achieved by using a demand factor, which is a percentage that represents the maximum load that is likely to be used at any given time. The demand factor is typically less than 100% because not all electrical equipment will be operating at its maximum capacity simultaneously. The NEC provides demand factors for various types of loads such as lighting, heating, and air conditioning. By using these demand factors, you can accurately size the conductors and prevent overloading. In addition to the NEC, other standards and regulations may apply to electrical installations. These standards may include those developed by organizations such as the Institute of Electrical and Electronics Engineers, the National Fire Protection Association, and the American National Standards Institute. It is important to be familiar with all applicable standards and regulations and to ensure that the electrical installation complies with these requirements. Finally, proper installation practices are essential for ensuring the safety and reliability of the electrical system. Conductors must be installed in accordance with the manufacturer's instructions and the NEC requirement. This includes proper termination, splicing, and support. Conductors must be properly terminated to ensure a secure and reliable connection. The termination method should be appropriate for the conductor size and type. Splices should be avoided whenever possible, but if they are necessary, they must be made using approved splicing methods. Conductors must be properly supported to prevent sagging and strain. The support spacing should be in accordance with the NEC requirements. By following these proper installation practices, you can ensure that the electrical system operates safely and reliably for many years to come. In conclusion, designing and installing an electrical system is a complex process that requires careful consideration of several factors. By understanding these factors and following the applicable codes, standards, and regulations, you can create a safe, reliable, and efficient electrical system. It is always recommended to consult with a qualified electrical engineer or a licensed electrician to ensure that all electrical installations are performed in accordance with the applicable codes and standards. The process of selecting the appropriate overcurrent protection for electrical conductors is paramount to safety and system integrity. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current in the event of an overload or short circuit, thereby preventing damage to equipment and minimizing the risk of electrical fires. The selection of overcurrent protection must be carefully coordinated with the ampacity of the conductors being protected, as well as the characteristics of the loads they serve. The National Electrical Code, or NEC, provides detailed guidance on the selection and application of overcurrent protection devices. Specifically, NEC Section 240.4 outlines the requirements for protecting conductors against overcurrent. The general rule is that conductors must be protected at their ampacity rating. However, there are several exceptions to this rule that allow for the use of overcurrent protection devices with higher ratings provided certain conditions are met. One common exception is the next size up rule, which permits the use of the next higher standard overcurrent device rating if the conductor ampacity does not correspond to a standard overcurrent device rating. For example, if a conductor has an ampacity of 22 amps, the next standard overcurrent device rating is 25 amps. However, this exception is subject to limitations, as the overcurrent device rating cannot exceed 800 amps unless specifically permitted by other provisions of the NEC. Another important consideration is the type of overcurrent protection device being used. Circuit breakers and fuses have different characteristics and are suitable for different applications. Circuit breakers are resettable devices that can be tripped manually or automatically in response to an overcurrent condition. Fuses are one-time devices that must be replaced after they have blown. The choice between circuit breakers and fuses depends on factors such as the type of load being served, the available fault current, and the desired level of coordination. In addition to selecting the appropriate overcurrent protection device, it is also important to ensure that it is properly installed and maintained. Overcurrent protection devices must be installed in enclosures that are suitable for the environment in which they are located. They must also be properly labeled to indicate their ampacity rating and interrupting rating. Regular maintenance, such as testing and inspection, is essential to ensure that overcurrent protection devices are functioning properly and will provide reliable protection in the event of an overcurrent condition. In the case of parallel conductors, the overcurrent protection requirements are slightly different. NEC Section 310.10H permits the use of parallel conductors under certain conditions, including that they are all of the same material, size, insulation type, and termination method. When parallel conductors are used, each conductor must be protected at its ampacity rating. This can be achieved by using individual overcurrent protection devices for each conductor or by using a single overcurrent protection device for the entire set of parallel conductors. If individual overcurrent protection devices are used, they must be sized to protect each conductor at its ampacity rating. The sum of the overcurrent device ratings must not exceed the ampacity of the feeder or branch circuit being protected. If a single overcurrent protection device is used for the entire set of parallel conductors, it must be sized to protect the combined ampacity of the conductors. This can be achieved by using a larger overcurrent device or by using multiple smaller overcurrent devices in parallel. The use of parallel overcurrent devices is subject to specific requirements outlined in the NEC. In summary, selecting the appropriate overcurrent protection for electrical conductors is a critical aspect of electrical system design and installation. It is essential to understand the requirements of the NEC and to carefully consider the characteristics of the conductors and loads being protected. Proper installation and maintenance are also essential to ensure that overcurrent protection devices provide reliable protection in the event of an overcurrent condition.